How do we represent data? In this lecture video, we'll trace raw observations to vectors, matrices, tensors, and embeddings. Everything an AI handles, text, photos, sound, or records, must be turned into numbers so models can compute. Representation is the bridge. For example, cat maps to token IDs, then an embedding vector. A photograph becomes a pixel array or tensor. A student record becomes a feature vector. A good representation preserves task-relevant information so the model can learn and reason. A feature is a measurable or encoded property of an object. For a student, we could pick feature 1 as hours studied, feature 2 as attendance, and feature 3 as prior GPA. Those three numbers together place the student as a single point in a three-dimensional feature space, which is what the model will work with. Here we formalize a single object as a vector, an ordered list of numbers that encode features. For example, student A might be represented by the list 8, 0.92, 3.6, where each entry is hours studied, attendance, and prior GPA. The length of the list, its dimension called n, is the number of features. Treating objects as points makes distance and direction meaningful. Stacking individual feature vectors produces a matrix. Each row is one observation, and each column is a feature. For m observations and n features, the data matrix X has m rows and n columns. For example, each student row records hours studied, attendance, and GPA. Much of machine learning starts from this simple rectangular structure. Labels like red, blue, and green must become numbers. If you naively assign red equals 1, blue equals 2, green equals 3, you create an artificial ordering the model can exploit. One-hot encoding gives each category its own binary coordinate. Red becomes 100, blue 010, green 001. Choose representations carefully because they inject assumptions into the model. Images are already numbers. Each pixel corresponds to a numerical value in a grid. A grayscale image is a height by width matrix of intensities. A color image adds a third dimension, 3 channels for red, green, and blue, so it becomes height by width by 3. For example, a 224 by 24 RGB image contains 105,528 numerical values. Language is converted in stages. A sentence is first split into tokens, for example, AI, changes, education. Then each token gets a unique integer token ID. Those IDs are looked up and turned into embedding vectors, dense numerical coordinates that place related words near each other in a learned space. The overall goal is to make linguistic relationships usable by mathematical models. Embeddings convert objects, words, images, users, products, even proteins, into learned dense vectors. Close vectors mean semantic similarity. Cat, dog, and lion cluster together. Car, truck, and bus form another group, and apple and banana sit nearby. In that geometric space, distance, angle, and direction encode relationships that models can exploit for search, recommendations, and analogies. Now that objects live as vectors, similarity becomes measurable. Euclidean distance asks how far apart 2 points are. The dot product measures how strongly 2 vectors point the same way. Cosine similarity compares their directions while ignoring length. Those numerical comparisons power retrieval, recommendations, clustering, and semantic search. Data in deep learning are multi-dimensional arrays. A scalar is a single number, 0-dimensional. A vector is 1-dimensional, an ordered list such as 2, 5, 8. A matrix is 2-dimensional, rows by columns, useful for data sets. A tensor generalizes these to 3 or more dimensions, for example, batch by time by features, which is how images, video, audio batches, and transformer activations are represented. Knowing shapes helps debug models. Neural networks work by repeatedly transforming representations. Raw inputs, pixels or tokens, become simple patterns in early layers, then higher-level features in middle layers, and finally a prediction. Importantly, the network learns these internal representations, not just the final answer. In transformers, those vectors are contextual. The vector for a word shifts with its surrounding words, so the same token can represent different meanings in different sentences. A model's success often hinges on how we encode inputs. Poor representations hide important relationships, make distances meaningless, and add noisy dimensions. Good representations, by contrast, make relevant objects separable, so similarity aligns with the task and patterns become easier to learn. The key point: choosing the right mathematical encoding can improve AI performance just as much as changing the algorithm. Everything in an AI system starts with representation. We turn a real-world object into features, then into vectors or tensors, learn richer internal representations, and finally predict or generate. Vectors give us geometry, matrices organize datasets, and tensors scale to modern models. Embeddings let models discover useful features automatically, so the core mathematical question is which information must be preserved for the task. So, that was just a high-level introduction to how we represent data. Each of these concepts require more deeper studies and learn applications.